In this video, we're going to discuss what happens if you use a weak acid that is both the acid and the base. So when you've got a polyprotic weak acid, you can lose the first proton, making a conjugate base. So our H2CO3 can lose one proton to become bicarbonate, and bicarbonate can lose a proton to become carbonate. But, well, it's a conjugate base and a conjugate acid. Bicarbonate is amphoteric. It can act as both a weak acid and a weak base. As a result, really two things are going on. We've got one thought process where it's reacting as an acid, and we have one thought process where it's reacting as a base. Now in this case, it's not just doing the full reverse. It's not H2CO3, H plus, and bicarbonate because, well, there's no H plus around at the moment. If we add pure bicarbonate, so sodium bicarbonate salt source, you get just the bicarbonate ion. That is our only starting source. And so really the reverse reaction that we normally write can't happen. When it's acting as a base, instead it's going to steal that H plus from water. As a result, we have to write our equation a little bit different. Our base is going to steal H plus from water, it's going to make some acid, and it's going to make some hydroxide. When we have a pure weak base in solution, this is how we have to think about going backwards for it. Well, that means we need a Kb. We need a K for this acting as a base. How do we get that? Well, remember that for a conjugate acid-base pair that are reacting, which is bicarbonate and carbonic acid here, that your Ka times your Kb must equal Kw. We know the Ka for the first step, or at least we can look it up. Ka1 for carbonic acid was 4.5 times 10 to the minus 7. We can use that to solve Kb for that same pairing. 4.5 times 10 to the minus 7 times the Kb must equal 10 to the minus 14. So we'll divide this onto both sides. Our Kb, 10 to the minus 14 divided by 4.5 times 10 to the minus 7, we'll find that's 2.22 times 10 to the minus 8. So we can find the Kb for our bicarbonate ion acting as a base to make carbonic acid. 2.22 times 10 to the minus 8. Let's investigate both of these. If our bicarbonate reacts as an acid, so our first line, then what's going to happen is I'm going to have initially 0.050 moles of the bicarbonate. It's going to create some H plus and some carbonate, but they'll start at 0. There'll be some change. I'll lose some of this. I'll gain some of my products. So I'll reach equilibrium. 0.050 minus x, x and x. Well, if we're doing that first step, treating it as an acid, Ka is super tiny, so probably we can assume that the minus x is insignificant. Simplifies our work, no need for a quadratic. 4.7 times 10 to the minus 11 must equal x for my H plus, x for my carbonate, my CO3 2 minus, divided by 0.050 for my bicarbonate. Rearrange, solve for x. In this case, our x should be 1.533 times 10 to the minus 6, giving us a pH when we take the negative log of 5.814. Now that's if this is only acting as an acid, but I'll just tell you, if you actually throw sodium bicarbonate into water, so baking soda, put some in water, it's basic. 5.8 is acidic. It's lower than 7, but the reality is it should be higher than 7. We do have to consider the fact that it's also acting as a base. And so to do that, if we thought, oh, well, maybe it's just acting as a base. After all, the equilibrium for Kb, 10 to the minus 8, well, that's larger than 10 to the minus 11. It looks like it's better at generating product when it's generating hydroxide than it is generating product when it's generating H+. And so maybe that's what's going on. Maybe it's just acting as a base, primarily. And we could imagine that. We could say, hey, initially there's 0.050 for our bicarbonate. Water concentration doesn't change. There'd be no carbonic acid and, well, no hydroxide from this source yet. There'd be some change. I'd lose some bicarbonate. Water wouldn't matter. I would gain some H2CO3 and I'd gain some hydroxide. Eventually reach equilibrium, 0.050 minus X, X, and X. 10 to the minus 8 is pretty tiny compared to our starting concentration, so I can probably safely simplify this again. 2.22 times 10 to the minus 8 must equal our carbonic acid, which is X, our hydroxide, which is X, all over our starting value for bicarbonate, 0.050. So this is if we're doing the equilibrium calculation for the base reaction. Rearrange, solve for X. We'll find that X in this case comes out 3.3 times 10 to the minus 5, which means the pH would be 9.523. Well, hey, that is basic. And I told you if you actually throw sodium bicarbonate into water, it is basic, but it's not that basic. Because really, both of these are happening at once. One of them's better than the other. As we said, just look at the exponent. 10 to the minus 8 versus 10 to the minus 11. The Kb tells us that the base reaction is better at making the products, which makes hydroxide, than the acid reaction is at making products, which is where we get the H+. But they're still both happening. So how do we find the actual reaction? Well, we have to think of the two reactions that are occurring, and they are combining. We have our first reaction, and then we have our second reaction. In this case, we can just think of the equilibrium process occurring here because these are going to all be based around our bicarbonate. In fact, we can combine these reactions by reorganizing and adding these together. Think Hess law style. My right and my left add together. H2CO3 plus bicarbonate must be in equilibrium with 2H plus bicarbonate and carbonate. Well, my bicarbonates would cancel out, and there's a combined calculation that says H2CO3 is in equilibrium with 2H plus and carbonate. I've combined the two processes, and each of these had a Ka associated with it. 4.5 times 10 to the minus 7, and 4.7 times 10 to the minus 11. Well, in the same way we can combine our equations, effectively multiply them together, I can do this to my Ka values. The K value for this combined equilibrium must be the product of the equilibrium constants for the two reactions I combine. Another way to think of this is that Ka1 was H plus HCO3 minus over H2CO3, and Ka2 was H plus carbonate all over bicarbonate. Multiply both sides of these together, your Ka1 times your Ka2 equals your two equations multiplied together, which again will cancel out your bicarbonates and give you H2CO3 on the bottom as a reactant, two H plus concentrations as a product, and a carbonate concentration on top as a product. So whether you think of this as adding two equations or multiplying the two equilibrium expressions, the net effect is that our H plus concentration squared times our carbonate concentration divided by our carbonic acid concentration must equal 4.5 times 10 to the minus 7 times 4.7 times 10 to the minus 11. We're required to combine the two different equilibriums that bicarbonate are engaged in. At the moment, however, we have three unknowns. So how do we simplify this down to something that we can solve? Well, anytime our bicarbonate was to break apart and make some H plus and CO3 2 minus, that H plus, effectively, where's it going to go? It gets passed around with water, but on balance, what effectively happens is we just have bicarbonates trade a proton. One of these trades over, that goes away, we get an extra minus. It's a little more complicated in how it passes through the water, but the net result is we end up with equal amounts. Because H2CO3 is being created in solution when a free proton shows up to attach to bicarbonate, and the only free protons are showing up when a bicarbonate makes a carbonate, they're 1 for 1. When two bicarbonates effectively dissociate and react, they'll create one carbonate and one carbonic acid. They do indeed mediate through water to do it, but the net result is that these two have to have the same value. And since we're doing a ratio, they cancel. Whatever amount they are, they will cancel each other out. This simplifies down to then just Ka1 times Ka2 is equal to the square of the H plus concentration. So take the square root. Our H plus concentration in this case becomes 4.599 times 10 to the minus 9. If you want to take negative log of that, that gives us a pH of 8.34. To find the pH of an amphoteric salt of a polyprotic weak acid, we're required to combine both the forward and reverse reaction in order to see how they will balance out with each other. Fortunately, there's not a lot of polyprotic weak acids. We won't focus on it too much, but it is not a simple calculation to start with. You can't just treat it as the acid. You can't just treat it as the base. You can't simply add and average the two. You're required to combine the equations and solve out the pH in this fashion.